inviting me here. It's been a while since I've been in the department. I was here 4 years ago, and I think it's been 15 years prior to that, and it was probably another 15 years before that. So it's hard to believe that it's been 35 years since I graduated. The campus looks completely different, although there are things that I recognize. Dinkman, Swanson, or Sorensen was, Sorensen or Swanson? Sorensen was New Science Building when I was here. Swanson. The geology. But it's great to be back. So I'd like to talk to you about some of the things that I've done. And you can't say that you are the only person working on things. I've had an army of graduate students and undergraduate students helping me. And these are some of the current ones. And I'll point out Kate Pauls. Kate's here tonight, and she's an alum of Augustana College, and 3 seasons in Argentina together. You really can't do things without your graduate students. So these are my colleagues at the University of Wisconsin. And just acknowledging funding support from the university as well as various entities of the National Science Foundation. My interest is the late Paleozoic Ice Age and looking at it in terms of understanding deep time climate change and trying to understand some of the drivers that were going on and causing climate change and glaciation and then non-glacial periods 300 million years ago or so. And at that time, all the continents were together. You've got Pangaea, which means all the continents. In the northern hemisphere, Laurasia, and my favorite, the southern hemisphere, Gondwana. So I'm going to be talking primarily about Gondwana, but I'll jump and just mention Siberia just a little bit. And to understand the late Paleozoic Ice Age, you really have to look at all the continents that were glaciated. And it really helps then by going from continent to continent to be able to correlate and to understand how big the ice sheets were. When did they disappear? Did they disappear at the same time everywhere? Was it diachronous across the continent? And then, of course, the students, and again, I'll point out Kate, who is currently a PhD student at UW-Milwaukee and graduated from here in 2011.
She's right here.
So right now, we've got projects going on in the Paraná Basin in Brazil, and then various basins in northern, central, and southern Argentina. But I've also worked in South Africa trying to understand the glaciation there. And obviously, I spent a lot of time and camping next to Bill in the Antarctic and with students, both grad and undergrad, over the course of my career. Australia, photos of Tasmania, but also Western Australia. And it's thought that during that time frame, Earth was experiencing bipolar glaciation. So if you want to understand the glacial history of the Earth at that time, you've got to go and look in the northern hemisphere as well. So I spent some time in Siberia looking at the deposits there. So this is a chart showing ice ages in Earth's history over the last 700 million years ago. And here we are sitting at times 0 with years on this scale, and then relative latitudes that the glaciers extended. So here we are sitting at times 0 and wondering what's going to happen in the future. Well, we can't look and know for sure what's going to happen in the future, but we can look into the past. And if we look into the past, around 300 million years ago, we have this major glaciation that's going on. It's known passionately as the late Paleozoic Ice Age. And it has a couple of early blips it gets well established during the Carboniferous, and then ends in the Permian, and then Earth is relatively unglaciated, or at least in terms of ice sheets, until we get to the Cenozoic glaciation. So we're going to focus in on the late Paleozoic Ice Age and that icehouse conditions, and then a little bit about its transition into a greenhouse Earth in the Permian. So the reasons why I'm interested in it, and anyone is interested in it, in part is that it shares some similarities between the Cenozoic and the late Paleozoic Ice Age. There are a lot of differences. The biggest difference, obviously, is that we had Pangea back then, and we don't today. But they're both long-duration glaciations, depending on whose time scale you use, whose age model. Sometime, and if you use the Devonian, it's starting in the Devonian, the late Paleozoic Ice Age can extend as long as 100 million years. Most people would put it somewhere between 60 and 80, but it really started, at least started to be glaciated during the latest Devonian. It's similar to the Earth today in that it's the only other time frame that we've got a complex biota on Earth. No other time frame, no other ice house has the same biologic history or a complex history as the Cenozoic does. It's just these two, the late Paleozoic Ice Age and the Cenozoic, that has those. It's also a time when glaciation was occurring when there was low carbon dioxide in the atmosphere, and a similarity is that people have thought that the late Paleozoic Ice Age was bipolar like the Cenozoic Ice Age. But I put a big question mark here, because there hasn't been a lot of work done in the Northern Hemisphere. Okay, we know a lot about it. We've been studying the late Paleozoic Ice Age for the last 90 years or so, but there's an awful lot that's not known. And these are the things that really are not very well established. There's a lot of things we think we know, and then the more we investigate it, we realize we really don't know that much. And a lot of what we thought we knew is wrong. So we don't understand the setting, the environments in which the glaciations was occurring. We don't really have a very good handle on the ice centers, although we're starting to get a better and better understanding of that. We don't know the timing very well. In geology, to understand the history, you really have to put a date on things so that you can put it not only in space, but in time. And the late Paleozoic Ice Age is really poorly constrained. And understanding how it relates to other global events. I grew up in West Central Illinois. I'm a first-generation non-underground coal miner. All my relatives were underground coal miners. That coal has been thought since the 1930s to be in part due to fluctuations in sea level. And those fluctuations in sea level are thought to have been driven by the waxing and waning of Gondwana glaciers. So we really need to get a better handle on how they're related. And then finally, is it a bipolar glacial event at that time? So what I'd like to do tonight is just tell you a little bit about the traditional view. I'd like to spend an awful lot of time talking about some criteria in terms of identifying glaciation, why that's important, telling you a little bit about our current view of the glaciation, and then trying to address some of the things that was driving the fluctuations of the glaciers and the end of that ice age. So traditionally, we jump to Gondwana, and we jump initially to Dr. Hammer and my favorite continent, Antarctica, because at that time the South Pole was located, well, it was actually located and drifting across Antarctica in this fashion and then off the continent. But Antarctica was centered over the South Pole, over the South Polar Circle, and it's thought that there was this massive ice sheet that extended outward from Antarctica, and then it fluctuated and shrank and liberated water as it shrank to the world ocean, and sea level went up and down. And so if we look at what's going on in this part of the world, instead of Antarctica, at least initially, what we see are cycles. This is from Pennsylvanian age rocks in Kentucky, and I pick it because it's a beautiful road cut, and you can start to see, if you start reading the rocks, you can see changes in sea level. And the way that we would look at changes in sea level, and your geology professors would look at sea level, is we'd go out and we'd look at the strata, and we would progressively try to identify what rocks were deposited in a non-marine setting. And the things that we would look for, we would look for evidence for organisms that live on land. So in this case, this is from South Africa, some vertebrate footprints. This is from one of Dr. Hammer's site on Graphite Peak, Listersaurus maybe. Here you can see the ribs. Here are some vertebrates. So if you see non-marine animals, you know you're sitting in a non-marine setting. If you see coal forms on land. It may be wetlands, but it forms on land. This little thing here is a root. These things are root hairs extending out. Here's another root. This is the root of the lepidodendron tree. Here's Antarctica, and here's a stump in a fossil forest. So if you see these things, you can identify the rock units as being non-marine. Versus if you start seeing marine fossils, so here are some brachiopods, and this is in Western Australia. All these knobby little things over here are a bivalve clam. It's about the size of my fist, called iridesma. And then down here, you can see the shells, and these are iridesma as well, and there's some pectin. But it's telling you you're in a marine setting. So you can go out and you can go through these units, and you can go layer by layer by layer, and you can identify whether they were deposited in a non-marine setting or in a marine setting. And when you do that for the strata of Pennsylvanian age in North America, you see this alternation between non-marine and marine, telling you that either the land surface is bobbing up and down, or the sea level is rising and falling through time. And if it's rising and falling, then you need a mechanism to produce that. And that mechanism, back in the 1930s, a guy named Harold Wanless and Shepard from the University of Illinois attributed that to the waxing and waning of glaciers in Gondwana. And since then, there's been a lot of work that's been done on the cyclothems and the coal-bearing units. And what they have identified is that traditionally, and that view is changing, traditionally, it's been thought that they represent between 100 and 200 meters changes in sea level. That view is changing, and we now know that that number is much, much lower. But that's what the traditional view was. And that was one of the things that drove the modeling of this huge ice sheet centered over Antarctica. And that those cycles had a duration where they alternated from marine and non-marine of 20,000 to 413,000 years, which are in the range of orbital cyclicity, which we'll talk about a little later. So all of that has given us this view of this immense ice sheet, because this is the size of an ice sheet on Gondwana that you need to be able to have 200 meters changes in sea level. But there are some big problems. It's really difficult to get an ice sheet of this size centered over Antarctica to get the moisture to be able to grow an ice sheet. And when the ice sheets get to be this size, they become incredibly stable. They don't fluctuate. So instead of having a big ice sheet that's really stable, if you want fluctuations to go on, you need to have smaller ice sheets that are more sensitive to changes in global temperature. But if you have smaller ice sheets that may be covering the same size, you obviously lose volume. So this is the traditional view, and the emerging view is more that we had a bunch of smaller ice sheets. Okay? So let me tell you about why they were originally identified to be these big ice sheets and the criteria. So these were the criteria that you'll find that all sedimentologists use to some extent. They've been used since the 1930s. They're still used today. The presence of something called dimictites. Dimictites are these poorly sorted deposits that have large clasts in them. They have sand, they have clay. So it's just this jumble of deposits. And those deposits, glaciers typically deposit things that are called dimictites. Grooved and striated surfaces, where it's thought that a glacier moves over and erodes the surface. Outsized clast, dropped by icebergs. Distinctive clast shapes and erosional features. Rhythmites, bars, if you've ever heard the term bars. And I won't talk about Gondwanites, but there's a whole slew of other things. So typically in the literature, when people see these rocks that look like this, these dimictites, they're automatically identified and interpreted to be glacial tills. And so you draw a ring around it if there was a glacier over this area. The only problem is there are a lot of other things that produce this type of rock. So here's one that looks like it's highly sheared, and we interpret that to truly be the deposits of subglacial activity. But there are other things, like this deposit over here in Tasmania, that ends up being bedded. And it's more characteristic of mud flows, debris flows, that may or may not have anything to do with glacial deposits. So if we strip the vegetation off the slough, the hillside on the slough, and it rained, we'd get a dimictite after the rainstorm. And then you get material that settles out of a freshwater plume entering into an ocean, that the freshwater rises to the top. It's carrying suspended material that extends out into the ocean, and the fine-grained material rains to the bottom, and icebergs then carry out bigger particles and drop them out. So this produces a dimictite, or can. This is related to glaciers, but the glacier doesn't have to have extended out here. So you could easily overestimate the size, and if you estimate these to be subglacial, and they're not, you've got glaciers everywhere, all the time, at the equator, at sea level today, and that gives you a false impression of the size of glaciation. Here are some more things. These are dimictites, but these are volcanic debris flows. They have glass shards in them. They're made of volcanic material. There's no evidence that they were deposited by glaciers, but they're dimictites, and they have been interpreted in the past to be subglacial deposits. Grooved surfaces, where it's thought that the glacier would move over and the boulders that it's carrying at its base would grind into the underlying rock and groove the surface. They do that. So anytime these surfaces have been identified, they're identified in the southern hemisphere as being subglacial. But there are other things. If you have large slide blocks that slide down a continental slope at any latitude, they produce a grooved surface. If you have icebergs touching the bottom, like here in McMurdo Sound, they produce a grooved surface. And although this is happening with glaciers somewhere, remember, icebergs make it as far north as New Zealand in the southern hemisphere. I think there have been icebergs that have extended off the coast of North Carolina in the recent past. There's no glacier nowhere near North Carolina. There are small glaciers in New Zealand, but not in the ocean. But if you saw this and said, aha, we've got a grooved surface, there was a glacier here. You grossly overestimate the size of the glaciers. Icebergs will transport large material in it. As that iceberg melts and accumulates material on its surface, or it melts out from the bottom and on the surface when it rolls over, it dumps coarse material into environments that have really low energy, where typically you would just have fine-grained material slowly settling from suspension. So you get these big clasts that suddenly appear within the rocks, and yes, icebergs do that. And here's one in Brazil that's piercing strata. And all of these are probably the result of iceberg activity, but sea ice transports material, and lake ice transports material. So here's some boulders in lake ice in Iceland. This was transported by sea ice on a tidal flat in Canada. Sea ice can pick up things that are as much as 6 tons in terms of weight, and they can transport deposit material. And this boulder we interpret to be sea ice rafted material. Vegetation rafts material. So here's along the shores of Lake Superior. Here's a boulder stuck in the base of some driftwood, another one. Here's some along the Ohio River. They will transport material and drop things in. So you have to be somewhat careful in what's dropped in. If you're close to a volcanic center, pumice floats. When it becomes waterlogged, it drops into the record. So you have to be careful. One diagnostic feature is clasts that have a certain shape, that have been truncated and have this bullet-shaped morphology with scratches on. And those are distinctive of being glacial. So if you can identify those clasts as drop stones or within a subglacial environment that you think subglacial, they're pretty diagnostic. Anytime you see rhythmites, these alternating layers that are fine and coarse, they've often been thought to be lake deposits that are the result of fluctuations in the input and then the turnover of lakes. And they're, in the rock record, used as strong evidence of glaciation. However, you get rhythmites in limestones that were deposited in tropical areas. So these are tidal rhythmites within a limestone. These are tidal rhythmites in Pennsylvanian rocks. When I was at Augustana College, we used to run out to Wyoming Hill and look at the rocks just outside of Muscatine. They're beautiful laminated silts and clays. And they're probably the result of tidal. They're not the result of glacial activity in Rock Island area during glaciation of the Rock Island area 300 million years ago. Okay, so we have to be really careful. So when we start looking at the record and we start really scrutinizing what the record is, what we find is we don't have this extensive, continuous glaciation of really large glaciers, but the record breaks down so it changes from continent to continent. So here are the various continents: West Central Argentina, Eastern South America and Brazil. Then in Southern South America, where Kate has done a lot of work in Patagonia, in South Africa, Antarctica, going over to Tasmania in Australia, Eastern Australia and Western Australia. The glaciation was not continuous. So here's our time scale going from 350 up to 260. The glaciers appeared and disappeared, so we have glacial intervals separated by non-glacial intervals. So it's not a continuous glaciation that was originally thought. Sometimes they're occurring over here in South America, while they're not occurring elsewhere. Sometimes they're occurring in Australia, and they're not occurring in Antarctica or in South Africa or in South America. So the record is much more complicated than we originally thought. And it's not this continuous glaciation. The record itself, how accurate is it? What's the fidelity of the record? There's this concept that as a glacier advances, it's eroding and destroying its entire record. And it does tremendous amounts of erosion. But when you get out in front of a glacier, especially in a glacial marine setting, beyond the farthest advance of that glacier, it's a record of deposition. So if you're looking at the record out here, you can have a really well-preserved, near continuous record. Even though sedimentation may be slow, there's very little erosion, at least glacially resulting erosion. When we look at the record, this is the record for eastern Australia in the Permian, the Mississippian, Pennsylvanian, and Permian. And it looks like this beautiful record of on and off. But this is a composite record. So this record is, this part of the record is from down here, and you're hopscotching around. So it'd be like looking at stuff in the Appalachians, looking at stuff in Illinois, running down to New Mexico, and coming up with a record for North America. It looks great, but you've only got a few meters of strata in any one place, and you're piecing it together. So it looks really good, but there's a lot of problems if you're using these composite records. One place, and why Kate and I are so interested in Patagonia, is that this is one of Kate's sections that she was working on for her master's degree. The strata are dipping there, and they run from the Mississippian up into the Permian, and you have 5,000 meters of continuous section. So you can walk through it. You can start down here and start in the Mississippian, and you can walk all the way through, and it's a glacial marine section, and you have an almost near continuous deposition that went on. The only big problem is dating it exactly, and that's a real big problem there. It's a beautiful record, but the control on time, we can put a gross estimate on when things happen, but we can't put the exact date on that. The glaciers there made it out to the continental shelf and then poured material into a deep water basin. So it's a beautiful record. There are other areas that we're just now starting to see good radiometric dates. Mostly the record in Gondwana is correlated based on pollen and spores, and it's great, but it's really inaccurate. So we need something that's better. In Argentina, a lot of correlation has been done not only by looking at pollen and spores, but looking at invertebrate fossils. And that's good, but everything is endemic to South America, so you can date it within a basin and correlate it within a basin, but it's difficult to do it from one place to another. But what we're now starting to find is we're starting to find a lot of volcanic ash, and especially in Brazil, and that's why Brazil is so interesting to us right now, because we can date the rocks there. And we found that in western Argentina, not in Patagonia, but northwestern Argentina, there's a lot of volcanic ash. In South Africa, there's a lot of volcanic ash. So it's starting to develop, and that record is getting better and better through time. So let's take a tour then of this glaciation. So glaciation really begins before this chart. There's a couple of blips in the Devonian just before I start this chart. And that's kind of start, stop. But the main glaciation of the late Paleozoic Ice Age starts in South America, and it starts at about 335 million years ago. And it's really only known from South America at that time. Rocks of that age in other parts of Gondwana are not glacial. So glaciation starts in this part of South America, actually this part of South America. And then by the time we get to the Mississippian-Pennsylvanian boundary, somewhere around 220 or 323 million years ago, glaciation just takes off and it becomes really widespread. And it becomes glaciation primarily in the westernmost part of Argentina. So this diagram that I'll show you is this area right here in westernmost Argentina. And this is an area where there are a lot of big, deep paleovalleys. And here's the edge of a paleovalley. This one's about 2 kilometers across. Here is the San Juan limestone over here. These are glacial and post-glacial rocks filling and lapping onto that basin wall. You walk across this pile and get to the other side, and this is the San Juan limestone. And here is the glacial at the bottom, and then post-glacial. And they're sitting there, and they're filling up these valleys, these very deep valleys that are up to 1,000 meters or more deep. So they're sitting in probably paleofjords, the deposits, and they all occur over in this region. Kate is really interested in this area over here, and there's been a lot of arm waving saying that, well, these are outlet glaciers. The problem with outlet glaciers is some of them flow in the wrong direction. They seem to be radial away from a highland, something called the Proto-Precordillera. And there's this little area over here that people have used to say the evidence from a paleovalley over here, they've used to indicate that there was this huge ice sheet sitting over here draining stuff off to the west. And when Kate and Levi Moxness last year went to this area and they started looking at it, here's the modern valley. This is a valley called Alta Melanzon. This is actually the Melanzon part of that paleo valley. And the person that worked on this said, oh, it's a beautiful U-shaped valley. It's glacial. And the only problem is that the granite walls disappear here and here, and this is fill. So you can't really say that that's the shape of the valley, because the valley could just as easily be V-shaped. And so you really need to look at the deposits within the valley and try to get a handle on how it was cut. So here's that valley, and we spent a lot of time looking at the rocks throughout this valley. And the person that looked at these, they saw these types of deformed material adjacent to big boulders. There was a boulder sitting here. And they say that, well, that's glacial shove. So when you go out and you look at the valley, here is the valley wall. And the stuff that's sitting on top of the granites and schist in here, the fill of that is a quartz arenite. And there are beautiful wave ripples in it. And there are things that tell you that there were these currents coming out and reworking them. And there are big alluvial fans that come out into this valley. And here you can kind of see it interfingering with some of that sand, which is a lake deposit. So these are alluvial fans prograding out into a lake. And here is another fan. The beauty about paleovalleys is oftentimes paleovalleys are the position of modern valleys. And so here's a little side valley coming into that valley, and here are the conglomerates, the alluvial fans that prograded out into that valley. And the valley's only, in some places, only 100 meters wide or so. And the valley walls are almost vertical. Here are large angular boulders. They are deforming sand from that lake. There are trace fossils in these sands that are squished, and it's not a glacial evidence. This is a landfall. It's a collapsed feature from the valley walls. And those little push structures, here's that one that was thought to be a glacial push. When you find and look at that, there's one here and there's one here. This boulder is dropped in, so it could be a drop stone. The only thing is 20 meters in this direction is a vertical wall. This is glacial material. These are things that are falling off the side of the wall into the lake deposits at the bottom. Other things that were thought to be glacial shove structures, turn out they are seismites. They're the result of failure and liquefaction and escape of water due to earthquakes. They're not due to glacial activity. So that whole concept of having an ice sheet sitting over here really falls apart when you look at the evidence. Okay. So that time frame was the same time that the glacial valleys in western Argentina were occurring. The glaciers disappeared in western Argentina, and they're gone. In this region, they haven't come back. When you go into the Andes a little ways away, yes, there's Cenozoic glaciation, but glaciers disappeared at the Mississippian-Pennsylvanian boundary, and they're gone for the next 320 million years. But when you look and you go from that area and you go actually a little bit farther away from the pole into the Paraná Basin in Brazil, Brazil's got glaciers and they're just cooking away. So that's a big question. Why was glaciation occurring elsewhere at a position just a little closer to the equator than they were in western Argentina? And the big question there is, how big were the glaciers? There's a lot of hypotheses. The biggest hypothesis, well, the two biggest hypotheses is that that Antarctic centered ice sheet extended all the way across Brazil. The other is that there was glaciers extending out of Africa, which was located here, and extending out into Brazil and making it all the way across into Paraguay and Bolivia. The other hypothesis is you had little ice sheets, little glaciers sitting along the margin of this basin and feeding ice into it. And that's really important because this is going to require a really large ice sheet, and the melting of that ice produces dramatic changes in sea level. These glaciers, they're big, but they're piddly when it comes to changes in sea level. You're talking about a half a meter or centimeters instead of tens of meters, depending on the size of the ice sheet. So another view of what one of those ice sheets coming into southern Brazil may have looked like. So this is in that inset. The other thing is it's thought that those glaciers advanced back and forth across southern Brazil into somewhere around about 292 million years ago. And within the last couple of months, we've dated some of the ashes, our colleagues at the University of California, Davis. And what we find is that those glaciers were older than the Permian. They are older than 300 million years. So the record is dramatically changing as we look at it. Here's some more of that succession. There are rhythmites. There are dropstones throughout this. But this is getting out into the basin. And this is often thought to be subglacial in here. But these are large slide blocks that are sliding down what's equivalent to a continental slope at the edge of a continental shelf, and not stuff associated with glaciation. So, we're really struggling with the size of these glaciers, and they don't appear to be as big as they were, and the timing is certainly not as long as it used to be. So now let's jump into the end of the Pennsylvanian and into the Permian. And at the Permian, there's evidence that there was glaciation everywhere in Gondwana, that it extended from southern Africa, maybe southern southern Argentina and Patagonia across southern Africa, Antarctica, India, and Australia. And it's thought that this was the most widespread point of that glaciation. And here's some stuff in South Africa, and the flow lines indicate that there are more than one glacial center, so it's not a big ice sheet extending out of Africa, but there are smaller ice sheets in Africa that are pouring ice into what's called the Karoo Basin. Then we jump to Antarctica, my favorite place. Okay? This is the area in here, the Transantarctic Basin, that Bill and I work on. Bill works primarily in the Triassic and Jurassic. I work primarily in the Permian in here. And this is the shape of that basin at the time there were glaciers. There are basement rocks that are striated. and glaciers do striate basement rocks. There are things that are highly sheared that look like they were overridden by ice. And here's another one. And when we start plotting out flow lines, what we find is that the glaciers, evidence for glaciers occur along the margins of this basin, but by and large they only occasionally extend into the basin and then flow down it. But what that suggests is that there was ice sitting over here and ice sitting over here. Instead of one big ice sheet that was located over the South Pole and extending out over Gondwana, Antarctica had multiple ice sheets, as did South Africa, as did South America. And then there's evidence within the basin that you get these wedge-shaped sandstones that show evidence for water coming out into this area and then beginning to flow, suggesting that it may be some type of meltwater plume. And then you've got these big stones that appear to be dropped in, sea ice, icebergs. But this is out here in the basin, and there's not a good set of evidence suggesting that the glaciers were overriding it, but they were sitting nearby. And then there's, again, lots of evidence. These are, here you can see a big block that slid. This is sliding down the basin slope, essentially equivalent to a continental slope. So there's a lot more than just glacial activity going on. Here's a person for scale. This person's only about this tall, though. So. And then there's another person up here for scale. And here's some folded strata, the result of sliding and slumping, but not necessarily glacial activity. So when we look at peak glaciation, this is what we think is happening, that there are lots of glaciers, and that they're growing and shrinking and responding to global climate, but not a single large ice sheet. Then when we go past peak glaciation, which peak glaciation is right in this area. Here is the Antarctic deposits, Tasmania. When we go past that, and there are also stuff in Australia in that peak period, when we go past that and we start looking into the later Permian, there are glacial deposits or things that have been interpreted to be glacial deposits sitting over in here. They're in the mid-latitudes. But at that time, here is the polar circle. The polar circle appears to be ice-free. And at that time, when you look at the deposits that were occurring in Antarctica, that was sitting within a degree or two of the South Pole, this is what you see. You see extensive deposits of sand and coal. The plants show good evidence for growth rings. So here's a big stump, and you can see the rings in it. And when you look at the rings which are preserved, there's no evidence for frost damage during the growing season. And geochemically, the type of growth that they appear to be experiencing is more typical of what you would see in the Pacific Northwest rather than in a polar setting, even though they're setting at the South Pole. So there's this big problem in why are there glaciers at mid-latitudes? They're small glaciers, and why wasn't the pole glaciated at that time? Okay, let's jump to the northern hemisphere and look at possible bipolar glaciation. During this time frame, during the Pennsylvanian and Permian, Pangaea was drifting northward, and it was drifting into the North Polar Circle, and Siberia ultimately drifted across the North Pole by the end of the Permian. And this is blowing up this area. There are areas where these yellow triangles are showing you where dimictites occur. These are all in deep water basins, and they're sitting adjacent to a volcanic arc. And when you look at the composition, these are the dimictites. They're all bedded. They have the characteristics not of glacial deposits, but of debris flows. You cut into them, and here they are. It's chock full of volcanic material. and the matrix is chock full of material that has blast shards. So we're interpreting these as being volcanic debris flows. And so we're no longer thinking that there are glacial deposits at that time, but all the material is coming from a volcanic arc into these deep water basins. So we would change what we thought was going on in the northern hemisphere, and at this point there is no evidence that there was bipolar glaciation going on. So let's look at some of the drivers, okay, because they're pertinent to us. First off, one of the early ideas was that, well, Gondwana and Pangaea moves around through time. So here's the shift of Gondwana across the South Pole being located here, and going from initially the Devonian through the Pennsylvanian into the Permian, and then even a little younger. And so it was thought that Gondwana just drifted over the pole and then off the pole, and that was why glaciation started, and that's why glaciation ended. But in a general way, that's true. It starts over here in South America, and then it progresses, and then it starts in Australia, and then it progresses across all of Gondwana, and then it disappears in Australia over here. In a real general way, yes, we need to have the continents in a polar position, but there's a lot more to the story. These little fluctuations in here are looking at cyclothems and the fluctuation. These are showing advance and retreats of sea level onto a continent. This one happens to be in Ukraine. This record's not accessible at the moment because of the problems in the Donetsk region of Ukraine. But they look very similar and are on a time scale very similar to orbital fluctuations. Remember, our pole is tilted away from the sun, so that gives us seasons. And sometimes the pole, over an interval of time, will move back and forth a few degrees. There's a wobble to the pole. And the Earth's orbit, sometimes it's more circular, sometimes it's more like a football. And all of those vary over intervals of time. The precession is 19 to 23,000 years. The obliquity, 41,000. The eccentricity, the change of the orbit, is on the order of 100 to 400,000 years. And it looks like they fit pretty nicely with this record, suggesting that yes, there is a component of these orbital parameters driving these ice sheets. But that's within a glacial period. They're not driving the beginning of glaciation and the end of glaciation. It's fluctuations like in the Pleistocene that we see in North America and in Antarctica today, fluctuations in the growth and decay of ice sheets because of changes in insulation. This is the long-term CO2 through the Paleozoic, Mesozoic, and Cenozoic. And the late Paleozoic ice age is a time of low CO2, as is the Cenozoic ice age. And then CO2 rises. A little more refined work. So this is the work of Isbell Montanez. She and her students are helping us with the work in Brazil. And she looks at soil chemistries, paleosols, and she tries to extract a CO2 record. And what she finds, these are the time frames when we've got glaciers, that there are dips in the record. So there are times of apparent low CO2. And then when we go into a non-glacial record, there seems to be a rise, and so forth. And that when we have this rise, that's when we come out of these glacial periods. So in here, there would be lots of these orbital fluctuations, but then we rise out of a glacial period during CO2 increases, fall back into a glacial period during low CO2, and then come out of it. Big problem is what's driving this CO2. She doesn't know, and I certainly won't suggest that I know. So just to sort of summarize all of it up for the late Paleozoic, it doesn't appear to be a single large ice sheet that lasted for 100 million years, but numerous ice sheets, small ice sheets, that had durations of a few million years, separated by non-glacial intervals of a few million years. They started in South America, in the Devonian, and ultimately ended in Australia in the Permian. When it ended in the Permian, Antarctica was in a polar position, as was South Africa, was just on the edge of that polar circle. Tasmania was just on the edge of it. Polar Gondwana was not glaciated at that time. So it's a really complex history. There are orbital parameters that suggest that there are fluctuations going on within that ice age. And it looks like it's CO2 that actually is what causes the beginning of these major glaciations at the end, and then the end of the whole of the late Paleozoic ice age. So ending here and then going into a greenhouse Earth. And again, our big question is what's happening here? So if we look at the CO2 record over the last 400,000 years, here it is fluctuating, and it's fluctuating with ice volume and temperatures. And CO2 never rises above 300 parts per thousand. We haven't been above this level prior to recently, since at least 18 million years ago. Here's the long-term record, going back into, here's the Eocene and the Oligocene and the Miocene, and here's approximately 300. There's a, I can't see it, little blip here in the Miocene, and then we've got to go back, this is about 18 million years, and here's the average, this line. We've got to go back into the Eocene and Oligocene before we see CO2s that we're now seeing in here. So if the late Paleozoic ice age is any indication, and we come out of these glacial periods when CO2 rises dramatically, we can apply that and then say, well, are we rising, because we haven't been at 400 for a very, very long time, and we're now at 400. Are we actually coming out of the Cenozoic ice age, which we're still in, and are we transitioning into a greenhouse Earth? So I'll leave it there. So thank you.